Good morning. Today I will be providing an overview of the development of space-qualified signal processing readout electronics for HAB worlds and the Origin Space Telescope Detector Arrays. My name is Dr. Tracy Jamison-Hooks, and I am the principal investigator for the NASA Strategic Astrophysics Technology Grant supporting this research. I'm pleased to be working with two of my graduate students, Oketa Basha and Abarna Karthikeyan, who have contributed significantly to this project. Today, my talk will cover the following topics. I'll begin with the science motivation behind the project, particularly its relevance to the search for habitable worlds. Then I'll introduce the enabling technology, microwave kinetic inductance detectors, and explain how they inform our signal processing approach. I'll briefly review current NASA missions that serve as a baseline for the Habitable Worlds Observatory, followed by an overview of the space-qualified hardware we're targeting. After that, I'll walk through the readout algorithm, focusing on the frequency transformation and channelization techniques used to extract MKID signals. Finally, I'll share our latest results, including a fully functioning embedded Polyphase filter bank. A key science driver for HWO is the spectral characterization of Earth-like exoplanets, which demands detectors with ultra-low dark count rates. Microwave kinetic inductance detectors have been selected for their suitability in this regime. The Probe Far Infrared mission for astrophysics, PRIMA, architecture utilizes MKIDs and currently serves as the baseline for HWO. Prima's ability to operate effectively in the 30 to 300 micron range, a largely unexplored part of the spectrum, positions it to bridge a critical gap in our ability to detect and characterize potentially habitable planets. Since HWO aims to detect biosignatures, it requires detectors with ultra-low dark count rates due to the extremely faint planet signal relative to the host star. MKIDs provide photon counting capabilities with dark count rates as low as 1 e to the minus 3 counts per seconds per pixel, enabling clean spectral measurements. High spectral resolution is also essential, with detectors targeting R equals 32 at 400 nanometers. Additionally, scalable readout electronics with high dynamic range and multiplexing density are critical for large format arrays. MKIDs uniquely meet HWO's demand for sensitivity, resolution, scalable readout, making them a core technology for future exoplanet discovery. In Peter Day's MKID paper, these figures help explain how the detectors work. Imagine a superconducting film as a quiet dance floor filled with perfectly paired dancers. Let me get my laser pointer. The Cooper pairs. When a photon hits, it's like someone suddenly breaking up those dancing partners, creating solo dancers called quasi-particles. This disruption changes the dance rhythm, which in MKID terms means the kinetic inductance of the film changes. The resonator acts like a tuning fork with a natural frequency that shifts when the dance rhythm changes. By sending a microwave probe signal through the tuning fork. We watch how the signal's power, right here, and phase, similar to the volume and timing of a musical note, shift in response to the photon's arrival. These shifts tell us a photon was detected, making MKIDs highly sensitive listeners for faint signals in the universe. This slide shows a schematic of an MKID array, showcasing their use of frequency domain multiplexing, a key strength of MKID technology. Each pixel is a superconducting resonator tuned to a unique microwave frequency, allowing high transmission outside its resonance so pixels don't interfere with each other. By probing the array with a frequency comb, one tone per resonator, we detect slight resonant shifts when photons are absorbed, identifying the hit pixel without crosstalk. Crucially, this approach lets us scale to thousands of detectors on a single readout line. And the more detectors we have, the more photons in spatial positions we can measure simultaneously, directly translating into richer, more detailed science data. This scalability makes MKIDs ideal for space missions like PRIMA and HWO. We're maximizing science output while minimizing mass and power is essential. To understand how we measure signals from the MKID array, we begin by focusing on a single detector. Each MKID has a resonator bandwidth of about 30 kilohertz, which determines how quickly it can respond and how finely we must resolve its signal. We use a high sampling frequency of 5 gigahertz, chosen to match the array's size and frequency spacing, ensuring we can accurately track tiny shifts in resonance. To achieve the required spectral resolution of about a third of the resonator bandwidth, we calculate the necessary number of samples and process the data in blocks on FPGA. This approach allows us to precisely extract the resonance frequency shifts for each detector, a process that can be scaled up to handle the entire MKID array. So in our example, we are processing blocks of 2 to the 19th samples continuously to obtain our science measurement. Now, let's discuss the critical algorithms that power the HWO MKID readout system, enabling accurate and efficient data capture and processing. The core component is the polyphase filter bank, which divides the wideband input signal into many narrow frequency channels with minimal distortion and high efficiency. Designing this filter bank demands deep expertise and careful use of computational resources. Complementing this is the pulse detection algorithm, which identifies and extracts the energy profiles of individual photon events by analyzing their shape and amplitude, allowing precise measurement of photon energies and arrival times. In addition, the tone tracking algorithm plays a vital role by continuously adjusting the probe tone frequencies to match each detector's shifting resonance, ensuring maximum sensitivity despite environmental or operational changes. Lastly, because cosmic rays can disrupt data in space, a dedicated cosmic ray mitigation algorithm detects and reduces the impact of these events, preserving the integrity of the measurements and minimizing false positives. Together, these algorithms form the backbone of the MKID readout. FPGAs play a critical role in over 95% of NASA and DoD spaceflight missions due to their customizable and reprogrammable and real-time processing capabilities. These onboard computers enable unique mission-specific signal processing algorithms essential for scientific measurements. The greater the real-time processing done on the FPGAs, the more successful the mission. Engineering expertise in FPGA design and development is vital, as demonstrated by their use in landmark projects like JWST, currently Prima, and now HWO. This expertise combines digital logic, signal processing, statistics, and hardware description languages such as VHDL, tailored for space flight standards. The growing demand for FPGA experts spans academia, industry, and specialized fields like this one, MKID Readout, which rely on advanced multi-rate digital signal processing. Similar FPGA skills are also highly sought after in high-frequency trading platforms, illustrating the broad and critical role of FPGA technology today. SpaceCube is the targeted hardware for the Prima mission and what we are using to baseline the HWO design. SpaceCube is a modular, high-performance computing platform developed at NASA Goddard Space Flight Center. It enables the integration of space-qualified FPGA with high-speed ADC DAC cards into a compact chassis. This architecture allows for real-time signal processing in space and supports data input through interfaces like SpaceWire. Designed for flexibility and flight reprogramming, SpaceCube supports a wide range of science and engineering missions, making it ideal for advanced applications such as this one. The space-qualified FPGA-based dual-chain MKID readout system continuously transmits and receives data using space-qualified DACs and ADCs at a high sampling rate of 5 gigahertz. Data is processed in blocks of samples to meet system requirements. On the transmit side, the IQ signals are generated by combining frequency tones using Chordic and the inverse polyphase filter bank, then sent out through the DAC via the RF front end to the MKIDs. The received IQ signals are digitized by the ADC and undergo a large frequency transformation in 2 steps: coarse and fine channelization. At each phase increment during the fine channelization, a cosmic ray removal algorithm cleans the data before it goes into the vector accumulate or coadd stage. Both the in-phase and quadrature channel outputs feed into the tone tracking algorithm, which keeps the system locked on the resonant frequencies of the detector. Finally, the coad and pulse detection data are transmitted via space wire for further analysis. This architecture enables efficient, high-precision readout suitable for space environment. And again, this system block diagram illustrates two signal chains. So if we're trying to get the frequency content of the MKIDs, and we know that the number of samples we need to process is 2 to the 19, why not just use a single large point FFT? Well, while such a large FFT would provide the ideal spectral resolution, like 488 kilohertz, it would provide a better spectral resolution than that. It's simply not feasible on the current FPGA hardware due to resource limitations. Instead, we are going to show you why we need to split this frequency transformation into two stages, coarse and fine channelization, making the processing more manageable. However, this approach, like if we were to use a large FFT, we have the challenge of spectral leakage. When a single frequency falls between the FFT, like you see here, its energy spreads across multiple bins, following a sync-shaped pattern, not just a simple 50-50 split. This reduces the tone detection accuracy. To address this, we minimize leakage using techniques like windowing and polyphase filter banks. It balances resolution with hardware limits through the two-step channelization, and we carefully align tones as close as possible to FFT bin centers to preserve signal integrity. MKIDs are densely packed multiplexed resonators. Fabrication variations produce gaps, so that frequency regions without resonators. This causes some MKID tones to fall between FFT bins, while in other cases, FFT bins are empty. Using a massive 2 to the 19 point FFT for perfect resolution isn't practical due to FPGA resource limits and wasted processing on empty bins. Instead, we start with a smaller point FFT for coarse channelization, where multiple tones can share the same bin, like kids sharing a room in a slumber party. To separate them, a fine channelization stage mixes down and applies narrow filters, isolating individual resonators. The polyphase filter bank further reduces spectral leakage by filtering around each FFT bin, and this improves tone isolation while preserving frequency content, even when tones don't align perfectly to the bin center. This figure compares the spectral response of a standard FFT on the top with the polyphase filter bank, or PFB, on the bottom. The FFT's frequency bins have high side lobes. We're showing two channels. High side lobes around minus 22 dB, meaning weaker signals near strong tones can be lost in the noise, even after averaging, making the FFT vulnerable to spectral leakage. In contrast, the PFB uses filtering before the FFT to shape the frequency response, greatly suppressing the side lobes and containing leakage. This enables detection of faint signals close to strong ones and allows tailoring the filter shape to mission-specific requirements. This improved spectral integrity is a key reason we use PFB in our coarse channelization stage, not just to split the spectrum, but to preserve signal quality and avoid misdetections, particularly because of the architecture of our MKID detectors. Major driver for choosing the polyphase filter bank for the coarse channelization stage. Okay. Our approach to building the polyphase filter bank in VHDL starts with creating a fixed point model in MATLAB Simulink to understand the theory and verify filter behavior before hardware implementation. We begin by designing a single low-pass prototype filter based on the required transition and stop band specs, which works for both a 4-channel and 1024 channel PFB. This filter is then split into its polyphase components, shown here as a color-coded matrix, where each row represents a subfilter, enabling efficient parallel filtering. After filtering, the signal goes through an FFT, in this case, a 4-point FFT. When the number of polyphase branches equals the FFT size, the system is critically sampled, a common efficient setup for real-time FPGA channelizer. I noticed some confusion around polyphase filter banks. People often focus so much on the filtering that they forget the FFT is still there, doing the essential frequency binning. So this slide is a simple but important reminder. A PFB isn't just filtering, it's filtering around each FFT bin. Imagine a plain FFT where each bin has a wide leaky response with poor side lobe suppression. The polyphase filter bank wraps a tailored filter around each bin, improving spectral containment and reducing leakage, which is crucial for detecting weak or closely spaced MKID tones. The FFT still does the main work of separating frequency components, but now it does so with a much cleaner, well-controlled bins. Now we scale to the hardware efficient implementation of the polyphase filter bank, whereby our filter coefficients listed here, these H's, are arranged in memory through in their polyphase components, and we use only one multiplication chain, only one subfilter row to service all 1024 channels. And we do so by using delays that are found here. And this architecture is thoroughly explained in Fred Harris's multi-rate digital signal processing book. And so this is the implementation, the final hardware efficient implementation that we used. What you are seeing here is the output from our working Polyphase filter bank embedded system developed by our interdisciplinary team at ASU. This team combines expertise from the School of Earth and Space Exploration, Fulton Schools of Engineering, and the School of Computing and Augmented Intelligence, SCI. Together, we've built a real-time embedded system where the PFB is not just simulated, but fully implemented in hardware and controlled through software. In this demonstration, a test frequency tone lands cleanly in the correct FFT bin with the start and stop, which is right here. This is the start and this is the stop. This is the image tone. If you don't know what image is, you might want to take my course, Signal Processing on FPGAs. So with start and stop signals marking the FFT frame boundaries, illustrating how the system windows and processes the input over time. This isn't just a working PFB model. It's a showcase of interdisciplinary engineering at its best, where science, computer engineering, and signal processing unite to create something innovative that transcends any single field, pushing the boundaries of all of them. So what is next? What is next is the rest of the algorithms. When we thoroughly test the finished testing and configuring and creating our test scripts for the Polyphase filter bank, we will move on to the fine channelization algorithm, and then we will carefully integrate cosmic ray removal, develop and integrate. We have already completed our averaging algorithm, which is our COAD. We need to develop the pulse detection and the inverse polyphase filter bank. Once you develop the the synthesis polyphase filter bank, it's straightforward to do the inverse. Okay, so we're very proud of the work so far, but we know that we have much more work to do. None of this would have been possible without the dedication of the students. This was student-led, student-done. They followed the learning path I set for them. I developed a course called Signal Processing on FPGAs, which laid the foundation for our achievements. These students embraced every challenge, starting each class with a brief mindfulness moment and tackling problems no one had solved before. They worked harder than they could even imagine. Honestly, none of us knew how it would turn out, including me. That's the essence of research, stepping into the unknown and creating something new together. My dad used to say that what made the difference between me and others who had it tougher was the encouragement he gave me and the push to go beyond what I thought was possible. Looking back, I see the same thing was true for these students. The support and guidance to manage their stress made all the difference. They blew past every expectation. It goes to show, with the right mindset and a little help, anyone can break through barriers and accomplish remarkable things. I'm really looking forward to working with you, and I hope that this gave you a really good overview of Habitable Worlds and the great task before us that we can all be a part of. Please continue to ask questions. And if you're looking at this through YouTube, hit the subscribe button so I can know that you are there and this is meaningful for you. Have a great rest of your day.